Hi there, this video is about redox reactions. So far what we've covered is oxidation numbers. Basically we've learned about charges, and what we're going to be doing today is actually tracking those charges and seeing who lost electrons and who gained electrons. Remember, in batteries what's happening is electrons are moving along the wire, and anytime you've got these moving electrons, it's electricity. Electricity is our whole part here. We're trying to create an electric current, and with an electric current we can do things with it. So we need to know where electrons are moving to and from, because when we know that, we know where electricity is, and that's our whole goal here. So with that, we're going to go to the idea of what types of reactions actually make electricity, and the answer to that is redox reactions. Redox reactions. Now redox reactions is actually a simplified version of calling it an oxidation-reduction reaction. So redox reactions include reduction and oxidation, redox reactions. Take a look at this one right here, which we've looked at before. We've got lithium. This is lithium, the atom. And as lithium is the atom, it happens to have this one outer electron. That one outer electron makes it kind of unstable, and we know that lithium is an alkali metal which would love to lose its electrons to have a full outer octet, which will just be that inner ring with two of them. To do that, it's going to give its electrons to fluorine. Fluorine's totally fine with that. He's highly electronegative, and he would love to take them on. So now that electron lives right here with fluorine. It no longer lives with lithium. Because lithium lost an electron, it lost negative things, it has a +1 charge. Because fluorine gained an electron, it has one extra negative thing, negative electron, it is an F1-. So we can see that there has been a transfer of electrons. The lithium has lost electrons, and the fluorine has gained electrons. In a redox reaction, somebody must lose electrons, and then somebody else must gain those electrons. And that's how we have a redox reaction. Specifically, oxidation means losing electrons. And reduction means you gain electrons. Here I can see lithium would be oxidized, and I would say that my fluorine is the thing that's reduced, because it gained electrons. I have two mnemonic devices here to help you with that, how to memorize that oxidation means lose and reduction means gain. This little guy right here, he's so cute. He's a teeny tiny little lion, and his name is Leo, and he goes grr. And that's because it goes lose electrons oxidized, gain electrons reduced. Let me say it again. Lose electrons oxidized, gain electrons reduced. You might be thinking, I don't really like lines. That's not a very good one. Stop, give me another one. This is a picture of an oil rig. And perhaps this one will work better for you. Oxidized is lose, reduction is gain. Try that again. Oxidized is lose, reduction is gain. I would suggest picking one of these mnemonic devices, I still use them today, and write them in your notes. If you need a recap on what it is, just kind of rewind the video and take a look. Okay, now what I'm going to do is open up to my thing to look at some practice problems here. So here I've got two practice problems. And what we're going to do is decide what specific element has gained electrons and what specific element has lost electrons. And the only way to do that is actually assign oxidation numbers, which is why we did what we did on Monday. So let's take a look. First step is we should assign oxidation numbers. So here goes. Here's magnesium. He's all by himself. He doesn't have a charge. He is a 0. He hasn't lost nor gained electron. He has no charge. Now I've got copper here. He's up to chlorine. That's when I have to start looking at the periodic table. Easy way to go would be chlorine. Chlorine is right here. This is a 0, -1, -2, -3, so chlorine is a -1. Chlorine is a -1. 1 times a 2 gets me a -2 total, which means copper over here has to be a +2. He's a +2 in order to balance out the -2 to make it a 0. Next over here I've got magnesium. Well, once again, chlorine is a 1-. This is an ionic compound, so that's always 1-. 2 times -1 is a -2. Magnesium, it happens to be right here, which makes sense because this is a +1 and a +2. Magnesium is a +2 oxidation number. And then over here I've got copper all by himself. Remember, these are tricky. When they're all by themselves, they do not have a charge. They haven't lost nor gained electrons. They are neutral. 0. Okay, looking good. So now what I want to do is actually track to see who lost electrons and who gained electrons. That means I want to see who's different from one side to the other. Like, check out magnesium. Magnesium here is a 0, but on the other side he's a +2. He has definitely changed. He's going to either be oxidized or reduced. Let's find the other guy. So where there's one, there's another. Here's copper. He's a +2. And over here, he's a 0. He's changed. Take a look at chlorine. He's a -1, and he's a -1 over here. He hasn't done anything. He's called a spectator ion. He's just hanging out. He's not doing anything. Okay, so now we found the 2 guys who do something. You should always have 2. If you have more than 2, you probably did something wrong. And if you have less than 2, you definitely did something wrong. So, here we go. Taking a look at magnesium. He went from a 0. Perfect. Perfect number of protons and electrons. Moving over here, he's a +2. The only way you can become positive is if you lose negative stuff. He lost electrons. He lost 2 electrons to do that. If you lose electrons, you are called oxidized. Magnesium is oxidized. Which means on the other side, I've got copper 2+, going to a 0. The only way to go from a positive to a 0 is if you gain electrons, gain negative stuff. Gaining electrons means you're reduced. Copper is reduced. Magnesium is oxidized, copper is reduced. All right, let's go to the next one. Why don't you pause it and try to do the oxidation numbers here, and then if you feel good about it, zoom ahead and see what I got for oxidation numbers. If you're not feeling good about oxidation numbers, I'm going to talk about it right now, so you can listen. First thing I'm going to do is look at AgBr. I see it's an ionic compound. I know that because it's a metal. I'm going to hit up Br. I like to go negative first. It's usually easier. Here's my bromine right here, and he's in the -1 lane. Nice. I'll call him -1. Silver, then, in order to balance it out, has to be a +1. I could double check that by looking at silver's in the middle here, which means I have to go to the back of my periodic table and look in the middle of the section of the back of the periodic table. And you'll see silver listed as a +1. Going to the next part here, chlorine, he's a 1-. I know that. Whoop, I'll put it up here. I know that because he's in this column right here, 1-. Calcium, 2 times a -1 makes a -2. Calcium is a total of a +2. +2. Looking good so far. Going over to the other side, chlorine's a 1-. We just covered that. That means silver's a 1+. To the next eye, bromine, we covered he's a 1-. So calcium over here, 2 times 1 is a -2. That means this has to be a +2 in order to equal a total of 0. All right, we're looking good. Hopefully you catched up back in the video if you scanned ahead. Now our job here is to decide, is this a redox reaction? Have electrons move from one side to the other? I'm going to look for somebody who's changed. Here's silver right here. He's a +1. On the other side, he's still a +1. No change. Bromine right here is a -1. On the other side, he's a -1. No change. Calcium right here is a +2. On the other side, he's a +2. No change. Chlorine is a 1-. On the other side, he's a 1-. No change. No one has changed oxidation numbers. That's a key part here. There's no change in oxidation numbers. Which means, has anybody moved their electrons around? Has anybody given up electrons and taken electrons? No. There is no transfer of electrons. Which means this is not a redox reaction. A redox reaction is one where somebody has lost electrons and gained electrons, a transfer of electrons of some kind. This has not happened here. This is not a redox reaction. In fact, if we think back, I know this is going back, what type of reaction do we have here? There's synthesis, decomposition, single replacement, double replacement, and combustion. Can you remember which one this would be? That's okay if you don't. This one happens to be a double replacement reaction. This is a double replacement reaction. I know that because it's compound plus compound. Does this double switcheroo to make compound plus compound? Double replacement reaction is the only one that is not a redox. All these other ones are redox. So if you're ever asked to find something that's not a redox reaction, you're going to want to look for that double replacement reaction. Hope this helped.